Okay, this is the fourth in a series of short videos where I'm discussing blocking probabilities and switching. And in this video, what I'd like to do is I'd like to take the example of a three-stage Clauss switch and show you how to apply the an approximation for the blocking probability of any path through this switch. First thing I'm going to do is I'm going to choose a switch design. I'm going to choose an 8x8 Clauss switch where big N is 8, obviously. That's the number of inputs and the number of outputs. I guess I want 4 of them here. And little n is 4, meaning, and little k is 2, meaning all of the stage 1 switches are 4x2. The stage 3 switches are 2x4. And I'm going to go ahead and wire this up, top to the top, bottom to the bottom, top to the top, bottom to the bottom, like this. Okay, so here's the wiring, the internal wiring for this switch. And what I want to do is I want to convince you that any given path through this switch, so for example, if I want to come in on input number 3 and go out on input number 5, then what I've got is I've kind of got a situation where I've got an input and I've got two different parallel paths that I can go through. I can go either this way or this way, and each of those parallel paths is made up of a series connection. Okay, so this is the topology of this switch. Okay, and if I know the blocking probability of each one of these separate little paths, then I can calculate, at least approximate, the blocking probability of this whole switch in going from some given input to some given output. Okay, and so I know how to do this because I think I just solved that in one of the last examples. I have two parallel paths, each made up of series connections. And in, let's see, in the previous video, we just did that problem. We solved this case right here. And this case gave a blocking probability of 1 minus the quantity 1 minus p squared, that whole thing squared. And that's when all of the blocking probabilities were equal. And that's what I'm going to write now. So I'm going to say that p block is equal to 1 minus p squared quantity squared. The first square comes from, the square on the inside comes from the fact that we've got two paths in parallel. And this square on the outside comes from the fact that we've got two paths in series. So this is the parallel two in parallel. And this 2 is 2 in series. Why did we have two paths here? Because we had two center stage switches. Okay? If we have n center stage switches, then we're going to have n parallel paths. How many center stage switches do we have? Well, each of these switches at stage 1 is little n by k. N by k. And it's that k value which determines the number of center stage switches, because the number of outputs on each switch at stage 1 is equal to the number of switches at stage 2. In other words, for the general case, we have the following blocking formula. It's 1 minus p. Let's see. This series is still just 2 in a series because it's a 3-stage switch. Okay, so this outer 2 still remains, but it's this inner one that gets replaced by k now. Instead of having k equals 2, this is the case k is equal to 2 because of our original design. And then the whole thing squared because of the due to 3 stages. Okay? And so this is our blocking probability of our three-stage Clauss network given K, and also given the blocking probability of any one of these links. Okay, and by symmetry, we're going to assume they're all the same. Furthermore, we're going to assume that they're all given by the space expansion factor here. And so recall that the space of expansion factor is K over N. And so in this case, our case, K over N is 2/4, which is 1/2, meaning that space is not expanded, it's actually contracted. And we had 4 inputs with only 2 outputs. And so what we're going to do is we're going to assume that there is a 50% probability that one of these paths is blocked due to this expansion factor here. And so the probability is okay, the probability that any one of these paths is blocked is going to be the product of the probability that the input line needs to be used, okay, divided by the space expansion factor, okay. First of all, the probability that the internal path is in use is the probability that we have to care about that path at all. And so we're going to assume that P is equal to P in divided by K over N. Okay, and when we have a large K over N, that means we really did expand. That reduces the probability of a block. Whereas a small K over N, like we have, increases the probability of a block because it's in the denominator. Okay? So this is how we're going to characterize these individual p-values here. Okay, so this is Pn is the probability that the path input is needed, and this denominator is the space expansion. Again, if we have fewer, if K is less than N, then that increases the probability of a block because we have a smaller number in the denominator. Okay, and so finally, if I can squeeze it in here, P block is 1 minus P input times N over K to the kth power quantity squared. So this is what we're going to use for the blocking probability of a three-stage Clauss switch. Okay, and it depends on N, it depends on K, and it depends on the probability that we need to use that path in the first place. Okay, I will show you how to apply this in the next video.